Welcome. In this video we begin Chapter 2, a primer of mathematical writing, and in particular we look at Section 2.1, Mathematical Writing. This is our first section on writing proofs, and in fact I will take 2 videos to cover Section 2.1, so this is the first of 2. In this video we look at a first proof and we examine what it takes to write a proof, and then at the end we will look at several more proofs pretty quickly to establish a feel for how to write proofs. Is the following claim true or false? Claim: if n is odd, then n squared minus 1 is evenly divisible by 4. What do you think? Maybe try some examples. So we have to put in an odd integer. Oh, and since I'm talking about odd or even, then we know that I'm talking about the variable n is in my set of integers. If n is odd, then n squared minus 1 is evenly divisible by 4. What do you think? If you try 1, 3, 5, 7, try some odd numbers, what do you get? Well, it looks like if you try a few odd numbers, everything that you get out, n squared minus 1, is evenly divisible by 4. We don't really see any counterexamples. So if we try to find a counterexample, we'll be out of luck. You just can't do it. So how do we prove that it's actually true? So here's our idea. Pretend that we are writing to a skeptical reader. This skeptical reader isn't irrational or stupid. They just suspect that the statement is false. You are writing a letter to a skeptical reader, to a person who you need to convince that this claim is true. 3 steps to writing a proof. So first of all, identify the relevant definitions. We must agree upon definitions for the proof to be meaningful. Now in the claim, there are 2 terms that we use. One is odd. An integer n is odd. Here's our definition. If n equals 2k plus 1 for some integer k. So how about 13? Is 13 odd? Well, I can write 13 as 2 times 6 plus 1, where 6 is an integer. So this establishes that 13 really is an odd integer, just in case you had any doubts. What about 10? Now 10 I can write as 2 times 4.5 times 1, but no, 4.5 is not in my set of integers, so this does not show that 10 is odd. The other term that we have in our claim is evenly divisible by 4. What does that mean? An integer n is evenly divisible by 4 if n equals 4k for some integer k. So, for example, 36. Is 36 divisible by 4? Well, can I write 36 equals 4 times something where that something is an integer? Yes, I can. Step number 2. Now that in 1 we've established the definitions, step number 2, let's write the hypothesis and the conclusion using those definitions. My hypothesis was that n is odd, and the conclusion was that n squared minus 1 is evenly divisible by 4. So I can write the hypothesis, n equals 2k plus 1 for some integer k, and I can write my conclusion, n squared plus 1 equals 4k for some integer k. Now, these won't be the same k's. These are 2 separate statements. And then step number 3. Let's write a letter, quote, letter, to the skeptical reader, establishing logically and rigorously that the proposition must be true that no counterexample exists. Here's what it says in the book. It is useful to think of this correspondence as a set of real instructions between 2 real people and not some abstract nonsense. A proof is not just a sequence of symbols. A proof is communication. It's one person convincing another that a certain claim is true. Let me write this out. This is a good thing to remember. Proof is communication. When you are writing a proof for me in my class, you are writing to me. I am the reader of your proof. So I am going to be I don't know that I'll be skeptical, but I'll be a very close reader and see what you say. Is what you're saying true? When you write one sentence and the next sentence, does the second sentence follow logically from the first? You're trying to establish something. You're trying to communicate. So don't just use symbols, use words in your proof. And as our book likes to say, think of it as a letter even. Let's give this thing a try. Here we go. Claim, if n is odd, then n squared minus 1 is evenly divisible by 4. A good way to begin, a standard way to begin proofs, is using the word let. Something like, let an odd integer n be given. The reason we do this is because we are establishing a variable n, and I'm telling the reader what n is. N is an odd integer. And I'm establishing the hypothesis. So I'm declaring a variable. I say, hey reader, as I write to you, I'm gonna be using this letter n a lot. And whenever you see this letter n, just know that n really represents an odd integer. Let it be given, just something. It's some odd integer. The second step, immediately after that, is to apply the definition. Since n is odd, what does that really mean? It really means that n equals 2k plus 1 for some integer k. These are always the first two steps of a proof. You establish a variable and the hypothesis. Then you apply a definition for any terms that are in that first sentence. After that, we look to the conclusion of the claim. My conclusion says something about n squared minus 1. It says that it's evenly divisible by 4. I want to show that n squared minus 1 is evenly divisible by 4. Show that n squared minus 1 equals, by definition, equals 4 times something. I won't write k in there, but just some integer in there. Can I do that? Can I write n squared minus 1 equals 4 times something? So the conclusion is about n squared minus 1, so let's start working with that. I write down n squared minus 1, and I notice that n, I already know something about the n. The n is 2k plus 1. So I can substitute 2k plus 1 for the n. Now, we simplify just with some algebra. I can expand the square, use FOIL. I can simplify with a little more algebra. And what do I want to do next? Do you see that? Now, it might be tempting, there's a common factor of 4k. It might be tempting to write 4k times k plus 1, but that's actually not what I want to do. What would I rather do instead? Look at the top. I only want a factor of 4 out. Because when I factor out the 4, now it looks like the definition I need at the very end. n squared minus 1 equals 4 times something. Now, that something, is that an integer? Well, I know that capital K, that is an integer. So k squared is an integer. So k squared plus k is an integer. So, in fact, there's this idea called closure. And closure says that if I take two integers and I multiply them, I get another integer. And if I add integers together, then I get another integer. So by the closure property, k squared plus k is an integer. Since k squared plus k is an integer, n squared minus 1 is evenly divisible by 4 by that definition of divisible by 4. And that is the end of the proof. I see my conclusion there, and I'm done. And we often use that solid square as an end of proof symbol. At this point, I strongly encourage you to, if you need to retrace through this proof. Pause the video and, without me talking, read through it line by line and see that you are convinced. If you are the skeptical reader, would this proof convince you? Is there something that is missing? Or see that it actually works and think about how you might write a proof like this for similar statements. All right, I will continue. Here's a few more definitions we will find useful. Even, an integer n is even if n equals 2k for some integer k. And general divisibility. an integer n is divisible by, say, 7 if n equals 7k for some integer k. Other divisibility definitions are similar. So n is divisible by 22 if n equals 22k for some integer k. So let's try some of these problems down below. Assuming all variables represent integers, let's see, 123 is odd because 123 should equal 2 times an integer plus 1. What is that thing? Maybe 61? And importantly, 61 is an integer. Now, why is negative 7 odd? Pause the video, actually. Can you write this one? This one's a little bit tricky. What do you think? Negative 7 is odd because negative 7 equals 2 times negative 4 plus 1. You still need the plus 1 at the end, so you actually need to overshoot in the negative direction. And negative 4 is an integer. We also need to state that. Why is 6m plus 3 odd? Well, look, I can pull out a factor of 2 from the for the first part, and it leaves a plus 1. That one's a little bit tricky too. Did you get that? And I didn't have enough space to write it, but I also probably ought to have and 3m plus 1 is an integer. How about 4? Why is 2 times n plus 3m even? Because the thing in parentheses is an integer, again by the property of closure. 5, 7 plus 42a is divisible by 7 because it equals 7 times 1 plus 6a, and 1 plus 6a is an integer. And lastly, 14b plus 10 is even because I can factor out a 2, and what remains, the 7b plus 5, is an integer by closure. How about some more proofs? So, again, in these proofs, you may assume all high school algebra and the closure property. You don't need to convince your skeptical reader of those facts. The first problem I will go through carefully, kind of like I did for the first proof, and we'll see how that goes. Proofs 2 and 3 I'll go through a little more quickly. Hopefully we are starting to establish the idea by then. Claims 4 and 5, I will leave those as homework. I would like you to write those out fully and be able to show me that you know how to do those proofs. I will repeat the statements of 4 and 5 at the end of this video. Alright, the first claim. If m and n are odd, then m times n is odd. Do you remember how we started the first proof with the word let? What will I want to let this time? Let m and n be odd integers. Now I need 2 variables at the beginning of this process, and they're both odd. So when I apply my definition now, I'm going to apply the definition of odd to m and to n. So m equals 2k plus 1, and n equals 2l plus 1 for some integers k and l. And I want to be sure to put different integers. I don't use k and k. I don't just keep reusing the k, because the m and the n could really be, or probably are, different odd integers. Now what? After the first 2 steps, remember, I've established my variables and I applied the definition. Now I look to the conclusion. How would I show that mn is odd? What I want to show is that m times n equals 2 times something plus 1, where that something is an integer. Can I do that? So let's look at that expression mn. mn equals 2k plus 1 times 2l plus 1. I know what m and n are from the previous line. Let's multiply those together. And now what? I'm only 1 line away. Can you see what's going to come next? I want to show that m times n is 2 times something plus 1. These first 3 terms, I can factor a 2 out of those. And I get 2 times 2kl plus k plus l plus 1. And now it's exactly in the form that I need. By closure, 2kl plus k plus l is an integer. Since 2kl plus k plus l is an integer, mn is odd, because mn has been written as 2 times an integer plus 1. End of proof. If n is divisible by 3, then n squared is divisible by 9. If you'd like, maybe pause the video, write out the first few sentences, see how you do on this proof. Alright, I'll begin. Let. What will I let in this case? How about let an integer n divisible by 3 be given? There's lots of ways that you can actually say this initial sentence. You might say, let n be an integer divisible by 3. That works. Or you could say, suppose that n is an integer evenly divisible by 3, or I don't know, lots of different ways. Or even just an integer n, you could write it a little bit more symbolically, like n is in the set of integers. Okay, anyway, we've established n, and we've established that n satisfies the hypothesis for the claim. Next, apply the definition. What does divisible by 3 really mean? N equals 3k for some k in my set of integers. Now, I've done the first two lines, the hypothesis and the definition. Look to the conclusion. What do I really want to show? I really want to show that n squared is divisible by 9, equals 9 times some integer. Can I do that? Well, let's start working with n squared. N squared is 3k squared. I can distribute my exponent by the laws of exponents, and I get 9 times k squared. And look, there it is right there. N squared equals 9 times k squared. Since k squared is an integer, n squared is divisible by 9. Now, just notice, it occurs to me that I am using words in this proof. At the very beginning I said, use words in your proof. There's not a lot of words, but I use the words that kind of help the reader along. The words then. Write that word down. Then this happens. Since. These are words that help the reader along and sort of establish the flow of the proof. When you write proofs for me, I really don't want to just see line after line of symbols and equations. Oh, end of proof. There we go. Solid square. Our third proof. If n is odd, then n plus 1 is even. Okay, by this point, you should be getting the hang of this. Pause the video, give this a try, and then unpause when you're ready to check the answer. Here we go. Let an odd integer n be given. Then n equals 2k plus 1 for some integer k. N plus 1 is 2k plus 1 plus 1. Let's do some algebra. That's 2k plus 2. What do I want to show? I want to show that n plus 1 is 2 times something. Do I have that here? Let's just factor out a 2. And this k plus 1, that is an integer. Since k plus 1 is an integer, n plus 1 is even. End of proof. The last two claims I will not prove right now. Again, these are for you for homework. Really do these. Write these out fully and show me that you can write out the complete proofs for these two claims. So that is the beginning of 2.1. In the rest of 2.1, we will see slightly different versions of proofs and maybe some different proof techniques, but this should give you a good start. So go to it and try your best.